Good morning. This is Naresh, chemistry faculty. Today we are going to discuss physical chemistry topic, ionic equilibrium. In ionic equilibrium, our subtopic is solubility product is the subtopic. So today we are going to discuss definition, applications of solubility product. So definition is very important to understand the applications. Applications are very important for JEE and NEET level exams. In applications, there are 6 applications, important 6 applications are there. 1. Relative solubility. 2. Common ion effect and simultaneous solubility. Selective precipitation. Effect of complex formation on solubility. Effect of pH on solubility. Separation of metal ion by sulfide and sulfide precipitation. So these are the 6 applications. All 6 applications are not possible to do in the same video. So that's why we can take the 2 parts, part 1 and part 2. So in the part 1 video, we are going to discuss about definition and the first 2 applications. In the part 2 video, we are going to discuss the remaining 3, 4, 5, 6 applications. Okay. So let's start with the definition. So let's start with the definition of solubility. Definition of solubility. To understand the definition of solubility, here I am taking the one important case, a sparingly soluble salt. So here I am going to take sparingly soluble salt to explain the definition clearly. So one of the important example for the sparingly soluble salt is AgCl. It is not completely soluble in the water, that's why it is called sparingly soluble. So AgCl, this solid when dissolved in water, first it is splits into Ag plus ion and Cl minus ion in water. So that's why you can represent like AQ, aqueous. So in aqueous medium, means in the presence of water, it splits into Ag plus and Cl minus ion. So initially it is splits into Ag plus and Cl minus ion, but at one certain stage, the reaction starts to move backward direction. The reaction starts to move backward direction and it is attain equilibrium. This is called ionic equilibrium. This is called ionic equilibrium of AgCl. So at this ionic equilibrium, at this stage, the amount of AgCl present in the solid form and the Ag plus and Cl minus they become as equilibrium state. So the undissociated form and dissociated form they become as equilibrium state. So this is the state we called as saturated state and the solution is called saturated solution. And the solution is called saturated solution. So saturated solution means when we can get the ionic equilibrium between the undissociated state and between the dissociated state, that the ionic equilibrium state is called saturated position and the solution is saturated solution. At this situation, there is no more salt is soluble. Okay, even if you add the salt, it is converted into ions, again the ions is converted into salt. Therefore it becomes as equilibrium, so there is no more ions are formed here. That's why it is called saturated position. So here there is no more salt is soluble. So at this situation, here I am going to take equilibrium constant K. So as we know that equilibrium constant is equal to molar concentration of the Ag plus and Cl minus products divided by molar concentration of the reactant. Here the reactant is AgCl. And the products are ions, Ag plus and Cl minus. Now take the AgCl on the left side. K into molar concentration of AgCl is equal to molar concentration of Ag plus into molar concentration of Cl minus. Here the amount of AgCl is almost constant. Why? Because it is sparingly soluble salt. Okay, very small amount of the salt is converted into ions. Very small amount of the salt. So alpha is less than 100. Here alpha is less than 1. So the solubility is very less. Therefore, the amount of AgCl is almost constant. The dissociation is less than 1. So very small amount of the salt is converted into ions. Therefore, here amount of AgCl that is not changes even after dissociation also. And K also constant. So it is constant. Here K term is constant and AgCl is constant. Therefore, we can take the new constant called as KSP. This is called solubility product. This is called solubility product. So solubility product. The symbol is KSP. So KSP is equal to molar concentration of Ag plus and molar concentration of Cl minus. So solubility product, so we can define like this. So solubility product is nothing but the product of, based on this we can define like this. The product of molar concentration of cation and anion. Cation and anion of a given salt. Of a given salt. We can define like this. So this is about the solubility product definition. Now the important point here it is, suppose in this case A, I am going to take the case B. So what is the case B is, instead of the sparingly soluble salt, I am going to take completely soluble salt. The salt which is completely dissociated into ion. So the one best example is NaCl. So in such a case, here it is convert into Na plus and convert into Cl minus. Here also ionic equilibrium is formed. Here also saturated solution is formed. And K equal to concentration of Na plus and Cl minus by concentration of NaCl. Therefore, in this case, here K into NaCl. So in this case, the concentration of NaCl is changes because it is completely dissociated. Therefore, the initial value here of NaCl and after the reaction, the amount of NaCl left is not same. Therefore, here the KSP is not significant. So KSP value, solubility product value is not significant for the solubility, completely soluble salt. If it is sparingly soluble salt, here AgCl is not completely soluble. That's why it is okay. It is significant. But whereas in this case, in the case of completely soluble salt like NaCl, it is completely soluble. It is completely dissociated into Na plus and Cl minus ions. Therefore, in this case, this value is not considered as a constant value and as a KSP value. Okay? So solubility product is there for both for the NaCl and AgCl, both for completely soluble salt and sparingly soluble salt. For both the salts, solubility product KSP value is possible to calculate. But in the case of completely soluble salt, this is insignificant. There is no matter of importance. Okay? That is a definition about solubility product. Right. Now we can go to the applications of the solubility product. The first application we can discuss now. So the application number 1 is about relative solubility of the salts. The first application is about the relative solubility of the salts. So, suppose here I am going to take 3 different salts, AgCl, AgBr and CaCl2. I am going to take the 3 different salts and both are dissolved in water, suppose. In the water, I dissolve the AgCl. In the water, I dissolve AgBr. In the water, I dissolve CaCl2. Now the question is, which is more soluble and which is less soluble? What is the order of their solubility? That is the question here. So, in order to know, which is more soluble? Suppose the soluble of AgCl is S1, the solubility of AgBr is S2, and the solubility of CaCl2 is S3. So, which is more value? S1 is more, or S2 is more, or S3 is more? Which is more value? That is very important to us, right? So, to know which is more value, so we must know the solubility of the compound. So, in order to know the solubility of the compound, to calculate KSP values they are very much helpful to calculate the solubility of the any salt. So, let's see how we can calculate. So, first we can take the note point here. Suppose AX and BY is the salt. So, for this salt, suppose solubility product is KSP. Then, how we can calculate the solubility? That is the point. If you see this note point, then it is very simple to compare the relative solubility. So, let's see how I do the calculation about the solubility finding of solubility by using KSP for the salt AXBY. So, first we can take the salt AXBY, which is dissociates into XAY plus YBX minus. It is dissociated into cation and anion. Therefore, solubility product KSP is equal to AY plus power X, BX minus power Y. So, the product of molar concentration of the cation and the concentration of anion. So, suppose it is soluble S times, then it is XS and it is YS. The solubility of cation is XS and solubility of the anion is YS. So, substitute those values here. XS power X, YS power Y. Therefore, KSP is equal to X power X, Y power Y, S power X plus 1. So, this is the relation between KSP and S. So, here by knowing the X value and Y value, suppose by the salt, suppose take this one, here AgCl. So, here in the place of A, we have Ag, in the place of B, we have Cl. So, in the place of X and Y, we have 1 and 1. 1 Ag and 1 Cl. Suppose then take the CaCl2. In the place of A, here Ca is there. In the place of B, here Cl is there. So, in the place of X, here 1. In the place of Y, here 2. So, by knowing the X and Y value, by seeing the salt, we can substitute here X and Y values. Okay, and KSP value is the experimental value. So, by knowing the KSP value by experiment and X and Y values, then we can get the S value. That is the method to calculate the solubility. Okay, so let's see by using this method how we can compare the solubility of these three compounds. So, if you see this one, then it is very simple to understand this note point also. For suppose experimentally it was observed that the solubility of KSP value of AgCl is 10 power minus 10 and AgBr is 10 power minus 20 and CaCl2 is 4 into 10 power minus 15 suppose. KSP values, experimentally it was observed value suppose. Then by using this experimental values I am going to calculate the solubility product. So what is the formula for solubility product? Yes, we already wrote that. KSP is equal to, here again I will take the formula. KSP is equal to X power X, Y power Y, S power X plus Y. So this is the formula I am going to use. That is the formula I am going to use to calculate the solubilities. So here KSP given as 10 power minus 10 equal to X power X. So 1 power 1, Y power Y. So 1 power 1, S power 1 X plus Y. So 1 plus 1. So S is equal to 10 power minus 5 here. So this is S1. S1 for AgCl. Now similarly for AgBr, 10 power minus 20 is equal to here also 1 power 1, 1 power 1, S power 1 plus 1. So S is equal to 10 power minus 10. And here Here 4 into 10 power minus 5 is equal to 4 into 10 power minus 5, 15 equal to, sorry, 10 power minus 15 is equal to 1 power 1 and 2 power 2 and s power 1 plus 2. Therefore, here s is equal to 10 power minus 5. So this is S2, this one is considered as S3. Therefore, in water, the solubility of AgCl is 10 power minus 5 and AgBr value is 10 power minus 10 and this value is 10 power minus 5. Therefore, it is very clear that what is the value which is more? S1. So clearly S1 is equal to S3 which is greater than S2. Means the solubility of AgCl and CaCl2 are equal and AgBr is less. That is the meaning. As per the KSP values. Okay. So these KSP values are just approximate values. Here I took just for explanation purpose. Okay. So to understanding this simply, just I took the KSP values like this. These are not exact experimental values. Okay. Approximate values I am taking here. So as per the KSP value I took here, this is the order of their solubility. Right. So this is the relative solubilities of the salt. Means which salt is more soluble, which salt is less soluble. To know this by using this application. Next, let's go to the application number 2, that is about common ion effect and simultaneous solubility. Application number 2 is about common ion effect, and simultaneous solubility. Simultaneous solubility. This is our application number 2. Common ion effect and simultaneous solubility is our application number 2. So let's see what is the meaning here. Suppose here I am taking the container. In the container, we can fill the water. So this is the water, and you can add the AgCl. Right? Therefore, and AgCl, the KSP value of AgCl here also I am considered as 10 power minus 10 mole square per liter square. Therefore, the solubility of AgCl, how we can calculate when it is dissolved into the water? How we can calculate? AgCl dissociate into Ag plus and Cl minus ion. So it is S times dissolved, it is S times. So KSP is equal to K, you can take the value directly. 1 power 1, S power 1 plus 1. So here KSP value given as 10 power minus 10. So S value is equal to 10 power minus 5 moles per liter. This is the solubility of AgCl when it is dissolved in water. Suppose in the same container, suppose I am going to add a strong electrolyte. Case a strong electrolyte means another salt which is completely capable to completely dissociate, like NaCl of the concentration 0.1 molar. So a 0.1 molar NaCl, suppose I am going to add here. Then how the solubility is changes of the AgCl? It is affect the solubility. If it affects, how it affects the solubility of AgCl, increase or decrease? That is the point I am going to discuss here. So here AgCl, because first we can add the AgCl. So AgCl is sparingly soluble salt. So convert into Ag plus and Cl minus ion, which is from the equilibrium state. Now we are going to add the NaCl also. So by adding NaCl, Na plus and Cl minus ion. Therefore here the KSP is equal to, as per the definition, concentration of Ag plus into concentration of Cl minus for the calculation of the solubility of the AgCl. This is the KSP formula for AgCl. Now here concentration of AgCl we don't know, so therefore it is considered as S. It is considered as S, so it is S. And concentration of Cl minus. Concentration of Cl minus is because of the AgCl it is S times form, and because of the NaCl it is 0.1 molar times form. Because it is 0.1 molar, NaCl is added to the container. Therefore it is S plus 0.1. In the previous case, the value it is S only, but in this case, it is S plus 0.1, and the KSP value it is equal to 10 power minus 10. So by here, it is equal to S into this S plus 0.1 value is considered as 0.1, approximately equal to 0.1, because AgCl is there in sparingly soluble salt, it is completely soluble salt. So because it is sparingly soluble salt, the value is very, very less, it is not completely soluble. So alpha is less than 1 here. Alpha value is less than 1. So the degree of dissociation into ions, alpha means the degree of dissociation of the compound into ions is very, very small, less than 1. So here it is less than 1, so this value approximately can consider as a 0.1, S plus 0.1 for our calculation purpose. So now S value here it is becomes as 10 power minus 9 moles per liter. So before adding the NaCl, S value what I got? It is 10 power minus 5. After adding the NaCl, S value is considered, you can got it is 10 power minus 9. So what happened? 10 power minus 5 and 10 power minus 9 means the solubility is decreases, it is the less value. Solubility decreases by 10 power minus 3. So because of the NaCl added here, the solubility is decreases. So because of the common ion, here Cl minus is common ion. So because of the common ion I added, then the solubility of the sparingly soluble salt is decreases clearly. This is mathematically also proved. So what is common ion effect? So what is the effect of common ion? So because of the common ion, it shows the solubility of the sparingly soluble salt decreases. This is the common ion effect. Now suppose consider the case B here. That is also a very important point. Suppose consider the case B. It is a weak electrolyte, suppose. So it is a weak electrolyte means suppose it is a NaCl. NaCl is the strong electrolyte and NaCl is the weak electrolyte. Okay, suppose you can add the weak electrolyte whose solubility product is suppose 10 power minus 20 suppose. Then in this case, what about the solubility of the first electrolyte and what is the solubility of the second electrolyte? Okay. Okay, so let's see here. So in this case, suppose it is, so we require the common ion also. So AgCl, sorry, there is no common ion. So we require the common ion. But in the case of strong electrolyte, we are going to take the weak electrolyte. So in this case, what is the common ion? In this case, the common ion is Ag. Ag is the common ion. Okay. So let's see how the solubility of the AgCl is affected when it is the weak electrolyte, which is having the common ion like Ag. So in this case, so it is dissociated into AgCl. So AgCl, then it is converted into Ag plus and Cl minus. Okay. So now in this case, both are sparingly soluble salts. Both are weak electrolytes. Means sparingly soluble salts are weak electrolytes. Both are same meaning. Okay. So now in this case, the solubility of the first compound is considered as S1, and solubility of the second compound is considered as S2. Okay. Now let's see here the KSP. KSP is equal to, now it is concentration of Ag plus and concentration of Cl minus. This is equal to concentration of Ag plus is S1 plus S2 also. Why? Because both are present in the same container. They are not in a different container. Both the salt are present in the same container. So S1 is from this side and S2 is from because of the second compound. So the total resultant Ag plus concentration is S1 plus S2 and Cl minus is only S1 because from the second compound there is no Cl minus concentration is present. Right. Similarly here also KSB is equal to concentration of Ag plus and Cl minus, and this is equal to S1 plus S2 into S2. Okay. So here the value it is 10 power minus 10 and here the value is it is 10 power minus 20. Consider this is as equation 1 and this is considered as equation number 2. Now we can take the ratio of 1 and 2. So I take the ratio 1 divided by 2. Then 10 power minus 10 divided by 10 power minus 20 is equal to S1 plus S2 into S1 divided by S1 plus S2 into S2. So then here S1 by S2 is equal to 10 power minus 10. So S1 is equal to 10 power minus 10 into S2. Now this S1 value we can substitute S1 in equation 1. Okay, or you can consider it is S2 equal to 10 power plus 10 into S1. So substitute the S2 value in equation 1. Because I want to calculate the solubility of AgCl. That's why substitute the S2 value here. Then what you can get? 10 power minus 10 is equal to S1 plus 10 power 10 into S1 into S1. So by solving this, you can get the S1 value. So S1 is the value of the solubility of the AgCl. So like that you can calculate the solubility of the AgCl like in this way. So this is called as simultaneous solubility. This is called simultaneous solubility. So in the weak electrolyte, if you add the strong electrolyte, then it is called as common ion effect. In the weak electrolyte, you can add the another weak electrolyte, and how you can solubility changes, then it is called as simultaneous solubility. These are the two important applications. Okay. So thank you for watching. Please like and subscribe to my YouTube channel. Okay. And the next remaining videos you can do in the next part. Thank you very much.